All right, so in this question here, I want to calculate the acceleration of the object from 0 to 3 seconds. Just a reminder, you should already have this in your note card, but just a little bit of a reminder that for velocity graphs, the slope is the acceleration. And just a reminder that the area under the velocity graph tells you displacement. All right, so we're going to use that fact right here. So the acceleration from 0 to 3 seconds, here we are at 3 seconds, and the point that we're at 3 seconds, rather the coordinate is at 3 seconds, we have a velocity of 2 meters per second. And when we start our stopwatch, we're actually going in reverse at -4 meters per second. So to get the acceleration, that's going to be y2 minus y1 over x2 minus x1. I'm just taking the rise over the run, and that's going to be 6 over 3, which is going to give me 2 meters per second squared. All right. Now we want to ask, is the object moving from 3 to 7 seconds? And we're going to describe what it's doing. So from 2 to 6 seconds, it's going forwards at a steady 2 meters per second. From 6 to 7 seconds, it's still going forward, but now you see that its speed's approaching 0. It's slowing down. So from 6 to 7 seconds, it's going forward and slowing down to a stop. Now let's get the displacement from 0 to 7 seconds. I'm going to use the area right here. So this is a triangle here. I notice that it has a base of 2. And it's got a height of -4. Here's another triangle. Here's a rectangle. Here's another, and there's another triangle. So I have 2 here. I have 1 here, 2 here, 1 here, and this has a width of 3. So my area, I'm going to use the triangle, which is 1/2 times -4 times 2 times -4. That's the triangle formula for the area. Plus my second triangle right here. So that's going to be 1/2 times 1 times 2 plus my rectangle, which is 2 times 3. And then finally my last triangle, which is 1/2, 1 times 2. And so when we work this out, this is going to be -4 plus 1 plus 6 plus 1, and that's going to give me 4 meters. I might label these little regions. So I'm going to call this region 1. This here is region 2. This here is region 3, and this here is region 4. And what I'm saying is I'm getting the area of this here, which is region 1. This here is region 2. This here is region 3. And this here is region 4. Those are the areas that I'm adding up. Now, does the object ever come to rest? I want to add one more thing to your note card, which is that for a V graph, V equals 0 means it's at rest. Okay? So to keep that in mind, what that means is this object does in fact come to rest. Let's write that down. So we'll say, whoops, it is yes at 2 seconds and at 7 seconds. And then when does the object ever change direction? Let's just remember, we have this in our notes already. This is moving backwards if you have it on a velocity graph, and this is moving forwards. This rule does not apply to position graphs. This forward-backwards rule for being above here or being below here, that only works for velocity graphs. So you notice right at 2 seconds, we're switching from going from backwards. We were going backwards, and then at 2 seconds we switch to going forwards. So the answer is yes at 2 seconds. And then F is a trick question. The answer is no, you can't ever get the initial position from a velocity graph. So let's add that to our note card as well. So I will say here, you can't tell the initial position from a velocity graph. Okay, so that's just another little thing for the note card that we should, well, note in our card. I guess I'm not trying right now, sorry. All right, so that is the answer to question number 5. We'll take a look at question number 6 in the next video.